Good morning, Mr. Suresh. I will be beginning with the part A of the assignment where I analyze the crystal sample provided in the class and identify its point group. So, few of the content is content in the slide is inspected by me, and the rest is sourced from internet. So, the crystal being provided to the monoclinic system provided. Okay. The specific crystal type as observed from morphology and symmetric elements. Let me classify it into the point group of 2 by m, which is also referred as CTH, which is shown in the part, slide 3 or 4. So I'll be explaining uh, each feature that support the classification, starting with the shape and symmetry element of the crystals. So starting from with the basics, the crystal has a monoclinic structure, system structure, and unlike cubic or hexagonal system, the monoclinic system is asymmetrical with the one angle referred to the beta, which is not 90 degree, and remaining two angles are equal and they are equals to 90 degree. In this case, the crystal does not have any uh, perfect or cube shape, but instead it take a prismatic form, which is like elongation with the one angle, right? This means it's a typically elongated from one uh, slightly flattened crystal with a well-defined basis on each side. Let's do the so next is crystal shape. So to find the point. So let's discuss about the point group 2 by m. Uh, there are two key symmetry elements to consider: a two-fold rotation and a plane mirror perpendicular to the axis. So, the two-fold rotational axis, this crystal, uh, the sugar or rock sugar, right? Uh, it has a two-fold rotational axis, which means it can be rotated by 180 degree along an axis, and it will appear identical uh, to its original configuration. This is a 180-degree rotational switch into the two-fold axis required by the point 2 by m. And the next part is the mirror plane, which is the essential part of 2 by m symmetry, again the rotation and the plane. Okay, so that a plane mirror divides the crystal into the two folded mirror halves like this, and uh, which can be viewed across this plane and are almost symmetric. This mirror symmetry is a core feature of 2 by m, which is which 2 by m point group, which further support the classification. To further talk about the point of 2 by m, in one of the system generally has three angles, as I explained earlier. The two angle equals to 90 degree, and third is not equals to 90 degree, which is okay, it's stretched diagonally, so it's not 90 degree, which is a monocline crystal system. And so this is the part, like the part I explained earlier about the part of the slide. And I don't have enough content.
So hello everyone, this is Bhupindra and this is the part B of the assignment. And in this part we have given a model named BATIO3 and the material, the CI file also. So we have to create the similar file in the software, Vista software, for the following compounds, which are CATE, GAP, K2O, CEO2 and AUZN. So let's begin. So let's open the file we have created for the previous atoms, molecules. So first we have to observe for CATE, right? So let's open it. So this is out layout of the Vista software, and this is CATE, which is a rock salt structure, which is simple cubic, in which these let's remove the extra elements first, then we will go for the element, the molecule further. Also remove these diagonal, the vertical extra bonds and atoms. So this is CATE, which is a simple cubic uh, rock salt structure, and we can start like it's a one unit cell. So in single unit cell, this is the position of Ca and Ta atoms. All the Ca are seated on the corner and face centers, and uh, the Te occupies the octahedral void inside the simple cubic structure. So this is the 3D model of the CATE structure, and uh, this is the best possible explanation for CATE I can give right now. Now moving to the second part of the assignment. Next part is inside the file is AUZN. So this is again the simple cubic structure, and and this gold atom is placed on the corners of the unit cell, and the Zn is placed in the in mid of the simple unit cubic cell, and each atom is connected with the 8 other atoms in. Next is CEO2. It's a fluoride structure. So again, there's a lot of extra atoms in the structure. So let's remove it. Oh, the extra parts are include. Also remove these bonds. So let's remove the vertical one also. Now we can freely rotate it. So it's a fluoride structure in which C atoms are placed on the lattice, and the other red atoms, which represent the oxygen, each placed in each tetrahedral word inside the lattice. So this is the visual representation of CeO2 in uh, Vista software I have created. This is how we can change the visual representation of the atoms, but I should go back to the ball and stick. Now going on this next element, which is GAP. So all the Ga atoms are placed in the lattice again, and it forms a FCC lattice structure, and all the other P atoms are placed on the alternative tetrahedral void inside the lattice, inside the FCC lattice. And this is how we can align all the atoms. Going on to the next one, which is K2O. It forms the antifluoride structure in which oxygen atoms are placed on the corners of the FCC and in the surface, midpoint of the surface, and the other atoms, K atoms are, it's a cation. It is placed in the voids inside the lattice structure. So there's a key.
So, hello. In this part, in part three, we will discuss about the generation of X-ray based on the chapter 13 from the Grey Longleaf textbook, focusing on the principle of X-ray production, uh, the types of X-ray radiation, and the absorption and the synapton radiation. So let's start with the basics of the principle of the X-ray generation. So the principles of the basic principles of the X-ray radiation, which include the production, the acceleration of the electron, production of electron, and hitting it with a metal. So there are three steps in the generation of the X-ray radiation. So first is the thermonic emission. So it describes about how we generate the electrons from the material which is heated at the high temperature, and it gets enough energy to get out of the atomic shell, and then the electron is released inside the tube, which carry a potential. So after that, the second step is the acceleration of electrons. So the emitted electrons from the cells of the atom are accelerated in the cell. It's basically a vacant cell, which carries a high potential, like in the kilovolt range. So higher the potential, the greater will be the speed of the electron produced, and it will consequently it will generate the high energy X-ray. So in the next slide, we will uh, discuss about the interaction with the target. So after finally these highly energy electrons strike with the target metal, usually which is a tungsten, due to the high melting point and as the atomic number, high atomic number. So when the electrons interact with the surface atoms of the tungsten target, there are two primary mechanisms of X-ray generation, and which includes the Bremsstrahlung radiation and the characteristic radiation. So we will discuss about the types of the X-ray radiation after the acceleration of electron from inside the cell and hitting on the target atom. So this Bremsstrahlung radiation and the character study. So it's a in the Brunstrom radiation, the highly high energy electron generated will approach the nucleus of the target atom, and they will slow down due to the field electric field, nuclear electric field, which deaccelerates. And I mean, like this deceleration of the electrons generates uh, the radiation, which is in the form of Brunstrom radiation. So this Brunstrom radiation produces the continuous uh, spectrum of the X-ray with the various energies. And the second one is the characteristic radiation. So in this process, when the electrons coming from the tube will collide with the inner shell of the electron with the target atom and will displace it. Okay? So when the outer shell electron fills this vacancy, it releases an X-ray photon with energy specific to the target nuclear targets target materials atomic number and structure, of course. So this is why it is called a characteristics X-ray, as and it is very it doesn't produce a very continuous spectrum of the X-ray. Rather, it produces a very discrete X-ray radiation. So the next one is, so this is the part six, seventh part of the slide. So we here we will discuss about the radiation, uh, about the absorption of the radiated X-ray. So the there are three types of no, it's, so the X-ray absorption is the essential part of the mechanism how the X-ray works. So there are three main mechanisms of how the radiated X-ray beams interact with the metals or the targeted material. So first one is the photoelectric effect. So in this photoelectric effect, an X-ray photon strikes in an inner shell of the electron and ejected, and the result and this results in a vacancy. And this vacancy is a in later filled with the outer shell electron, which will jump from higher state to lower state inside the vacancy, and which will emit the characteristic X-ray and will fall to the lower energy level, right? And second one is the scattering. So here an X-ray photon collides with the outer shell of the electron and ejecting it, while this scattering ejecting it, and the scattering of the photon will with reduced energy, and Crompton scattering often results in the lower energy and deflected X-ray photons. And third part is the pair production. The a high energy impact, a very high energy X-ray photon near the nucleus so so what is the pair production? When a very high energy X-ray photon comes close to the nucleus, so suppose this is the nucleus and this is the incoming photon of the X-ray, and it converts into the electron positron pair. So this process require extremely high photon energies, and which is less common in the standard X-ray applications. So it is not very much useful for us in this current studies. So this is the eighth slide out of nine, and here we will be discussing about the Sanathun tradition. So what's the Sanathun tradition and how it is produced? We will mainly focus on this tutorial. Also the practical application of the Sinathon radiation. So Sinathon radiation is generated usually when the electron travels at the nearly speed of the light using the uh, through the magnetic field, right? So this acceleration produces the extremely bright X-rays and valuable in the application that requires high resolution. So what's the practical applications of the synethon radiation? So synethon radiation is uh, mainly used in the field of physics, chemistry, and biology for the high resolution. Okay, so they are used to study the materials, atomic research, and chemical reactions. And biology structure in details also at the molecular and atomic level, providing and this provides the insights that are not possible using the conveyor like normal X-ray radiation or normal X-ray sources. So this is all about the 8th slide, and we'll moving to the next page, which is uh, where we will be discussing about the conclusion of the page. So this is the last part of the slide, and we'll get a summary and conclusion of the 7 slides we have read previously. So in this part, we will discuss the conclusion. So here, the first we discussed about the generation of X-ray, which involves the acceleration of generation of electron from material, and then we have to accelerate this particle or electron inside the tube, and then it will hit the surface of the tungsten, and there are two types of hit which will uh, produce the two types of the X-ray radiations. First one is the very the mm, discrete spectrum of X-ray, and the second is the continuous spectrum of X-ray. So the continuous spectrum is the Bromistolon, and the discrete is the characteristic, and there's a different mechanism in both of them. So one is due to the collision of like one is due to the deceleration of electron inside the nuclear field inside the atom, and second one is due to the excitation of electron in the inner cell, and it will create a vacancy, and then the electron from the upper surface will fill the vacancy and will radiate the X-ray intensity X-ray photons, and then it comes to the uh, mechanism of how these X-ray interact with the metals. So there are three types of interaction, which are the photoelectric effect, counter scattering, and the phase production. And finally, we discussed about the synchrotron radiation, which represents a high energy X-ray photon uh, X-ray source, opening door to the advanced research and application across the various electric field, and the ultimate purpose, the ultimate practical application of the synchrotron radiation is mainly in the resolution in physical application, and also in the molecular in the biology for resolution at a molecular or atomic level. So thank you, Mr. Sir, and this is all the all from my side from for the assignment part.